Hello, as I promised on the previous video, I will share a complete introduction on how to do the linear regressions model. This video is part 2 of 3 where I'd like to discuss about correlations, the development of regression model, and the interpretations of the model. In this video, I left you with the visualizations of scatter plot, box plot, and density plot. The scatter plots gives a good indications whether our dependent variable changes due to the changes of independent variable, while box plot and density plot can indicate if our data follows the central limit theorem or distributed normally. Remember, the linear regression model is one of the methods that is in the parametric statistic, and the parametric statistic requires the data to follow the normal distributions assumptions. Let's start our tutorial by doing the correlation analysis. Correlation is a statistical measure that suggests the level of linear dependence between two variables that occur in pair. In here, the pair is the maximum temperature and the minimum temperature. Correlation can take values between -1 to +1. If the maximum temperature increases along with the minimum temperature, then we can say the correlation is positive. If the other ways, then both has negative correlations. The closer the values to +1 or negative, the stronger the correlation is. In Rstudio, the correlation is done by the syntax, and the default syntax is person. Of course, we can specify the method of choose another correlation such as Kendall or Spearman. Our result is 0.87 means that there is a strong relation that increasing the maximum temperatures along with the increment of minimum temperature. Next part on this tutorial is the linear model. The function used for building linear model is lm bracket, and the syntax can be written as follows. The left part shows our y variable and the right part shows the x variable. Of course, we have to specify the data, so the syntax now where the lookup columns that have the same name with the variables mentioned in the syntax. As you can see in here, our model will take the equations of maximum temperatures equals to 10.7 plus 0.92 minimum temperature. Last part of this video is how to interpret our understanding and the diagnostic of our linear model by printing the model summary. This information is residue. Remember that the basic equations of a linear model doesn't contain only the x and y variable but also the residue in which the model cannot explain the variability of y values. Our model shows the residue ranges from about -52 to near 39 degrees, but the question is whether these residues cause our model to be statistically meaningless. Let's check the other informations extracted by the summary function. The coefficients consist of two elements, the intercept and the slope of the minimum temperature as the x variable. The following columns are the estimated values, standard error, t-values, and p-values. A larger t-value indicates that it is less likely that the coefficient is not equal to 0 purely by chance. So higher t-value, the better or the more reliable our model is. P-value is the probability that you get a t-value as high or higher than the observed value when the null hypothesis or the beta coefficient is equal to 0 or there is no relationship is true. So if the p-value is low, the coefficients are significant, and if the p-value is high, the coefficients are not significant. When p-value is less than significance level or less than 0.05, we can safely reject the null hypothesis that the coefficient beta of the predictor is 0. In our case, linear mode, both these p-values are well below the 0.05 threshold. So we can conclude our model, the parameter of our model is indeed statistically significant. The last part of the summary is the multiple r squared and the adjusted r squared. R squared tells us the proportion of variations in the dependent variable that has been explained by this model. As our values of r squared is 0.77, it means that the 77% variability in the maximum temperature values can be explained by the variability of the minimum temperature. Adjusted r squared, on the other hand, penalizes total values for the number of terms in your model. As you add more x variables to the model, it will usually increase the r squared. So it can be a good practice to look at the adjusted R square after the R squared to considered if we need to add more input data or no. To know if our model entirely can be used to fit or predict, then the F-test will answer it. Similar with the t-stat, the greater the F-statistic means the better, and significant p-values can be achieved by p-values lower than 0.05. So as our p-values is less than 2.2 exponent minus 16, then you can conclude by yourself, do we really can predict the maximum temperature based on only the minimum temperature values? And what's your reason? Share your thought on the comment sections. And okay, that is all for today's tutorial. I hope you find it useful. See you on the next part of this linear model series. Bye bye.